Okay, this is question number 12. Lots of different parts to this question. First, I have an RLC circuit. It has a resistor of 100 ohms. It has an inductor of 200 millihenries. And a capacitor of 3 microfarads. And this is all driven, it's a forced oscillation, a forced circuit with an AC generator that operates at 24 volts at 60 hertz. It has a maximum EMF 24 volts at 60 hertz. First, I want to know what is the maximum initial current of the circuit. All right, so what is the maximum current? Actually, I say initial, but really just what is the maximum current of this circuit? Well, as with all my circuits, Ohm's law applies. But as you recall, I not only have the resistance of this resistor, but I also have the reactance of the inductor and the capacitor. So this current is going to equal to the maximum EMF divided by the impedance. The impedance, remember, we got from combining our phasor vectors, is equal to R squared plus XL minus XC squared. And that's equal to 24 over 100 squared plus 75.4. I'll show you this. Let me just go and write it. Actually, let me go and do it down here. So XL is equal to omega DL, which is two pi F. That's omega times L. That's going to be 120 pi. It's 120 pi because I have 60 hertz times 2 pi is 120 pi times L, which is 0.2 henries. 200 millihenries is 0.2 henries. And that has a value equal to 75.4 ohms. Further, I can find XC. It's 1 over omega DC. That's equal to 1 over 2 pi F C. 1 over 120 pi. That's my angular frequency. C is 3 microfarads. This has a value equal to 884 ohms. All right, so each of these has certain reactance. I can put that in here. I get 100 squared plus XL, which is 75.4, minus 884. That's squared, and take the square root of that. Now, if I take this, I find that if I calculate that, the I max is equal to 0.03 amps. That's the maximum current that you get out of this circuit. Okay, now I also want to know what is the phase shift, because I can use the phase shift. If I know the maximum current, I know the phase shift, I can find the current at any particular time. So I want to find that phase shift. This comes about from our analysis of the phasors. Tan minus 1 XL minus XC over R. Remember, this is just simple vector math here. This is 75. Inverse tan of 75.4 minus 884 divided by 100 ohms. And that is equal to minus 1.45 radians. That's my phase shift. And I can use that now that I know the maximum current and the phase shift. I know the function, which is on your equation sheet, is equal to I sine omega dt minus phi. This is my function for the current in this circuit. That's going to be 0.03 amps sine 120 pi t minus my phase shift, which is going to be plus 1.45. And so that tells me my current. If I put that in for part that's part C, rather just writing that expression. And then for part D, if I want to know this at t equal 0.1 seconds, I just plug in 0.1 here for t, and I find that the current is 0.0298. So it's actually really close to my maximum current. So at 0.1 seconds, I'm right at the peak of the current. Okay, so that's my current at 0.1 seconds. Then I want to draw the phasors. Remember, just in general, be able to draw the phasors for these circuits. And remember that the inductance VL, the VL for the inductor, the voltage for the inductor, always leads the voltage for the resistor. And the capacitance voltage, VC, always lags. Remember that we had this mnemonic, Eli, the Iceman. All right, our current is always going to be in the same direction as VR. That's going to be our current. And the EMF of the inductor will always lead the current. So this is the EMF of the inductor. The EMF, that's what the E means. L means the inductor. I is the current. The EMF of the inductor is always going to come first. And the EMF of the capacitor is always going to come after the current. So this green represents the current. And the EMF of the inductor always leads. The EMF of the capacitor always lags. And then finally, what is the resonant frequency? Well, the resonant frequency is just equal to 1 over square root of LC. And so that's going to be 1 over the square root of 0.2 times 100, which is 0.22 radians per second. And at that resonant frequency, the current will be at its maximum value at that resonant frequency. And that maximum value will equal to the EMF maximum, which is 24 volts, divided by the resistance. So that would be 24 over 100, or it'd be 0.24 amps. So you see, if you actually operate at your resonant frequency, that is where your circuit is optimized for the frequency of the generator, then you get a much higher maximum current. So this is our maximum current in this circuit, but if it operated at the resonant frequency of 0.22 radians per second, it would have a much higher maximum current by an order of magnitude.